Now see this question. This question came in GATE 2009. It's about process state diagram. You see a process state diagram is given, and here there are you see 4 sentences are given. So it's like true or false. Okay. So you see what the states are: start state, ready state, running state, terminated state, blocked state. Okay. And these are the transitions: A, B, here it's C, it's D, this one is D, this one is E, this one is F. Okay. So on the basis of this diagram, we have to answer this question. Okay. Just we have to write true or false. Which statement is true, which statement is false. So you see here statement number 3, you see it's a preemptive scheduling algorithm. So is it true or false? Definitely it's true. Why? You see, because here you see there is a preemption from running to ready. A process is in running state, and you see that process went to ready. It's a RAM. Okay. And P1 is in running state. It means what? CPU is with P1. Okay. And P2 is doing nothing, but it's in a RAM. It means the state of P2 is ready state. So here I will write P2. Okay. But suddenly if the priority of process P2 becomes higher, or you can say that the time quantum of P1 expires, okay, then a CPU will be given to process P2 definitely. So maybe yes. So now CPU is given to process P2, and now P1 moves to the ready state. So it doesn't mean the task of P1 is completed. Here the preemption is happened. The task of P1 is not yet completed. P1 was running with the CPU, but suddenly the priority of P2 became higher. So now the CPU is given to process P2. So here you see process P2 is running. And what's the state of process P1? Since CPU is not with process P1 and process P1 is in the RAM, so the state of P1 is ready state. Okay. So definitely here you see the preemption is happening, because the CPU switched from process P1 to process P2, even process P1 did not get completed. Okay. So here you see preemptive scheduling. So statement number 3 is correct, and statement number 4 you see non-preemptive scheduling algorithm. So it's definitely incorrect. Okay. And moreover, when you will see there is a direct transition from running to ready, you just simply understand it's a preemptive algorithm. In case of non-preemptive algorithm, this arrow, this line will not be present. Okay. So we have analyzed statement number 3 and 4. So let's analyze first 2 statement, 1 and 2. Here you see. If a process makes transition D, transition D means what? This transition. It would result in another process making transition A immediately. It means what? If a process makes transition D, it means what? If a process from running state moves to the terminated state, it means a process from start state will move to the ready state. Is it correct? Let's analyze. You see, yes, a process is in running state. You see, it's a RAM, a process, suppose P1, P2. A process P1 is in running state. CPU is with process P1. Okay. And here you see it's a hard disk. In hard disk there is one process P3. Okay. So you see, if the task of process P1 is over, it means what? Process P1 is terminated. So process P1 will make transition D from running to terminated state. So it means what? The process control block of process P1 will be deleted. So here I will delete process P1. Okay. Yes. And you see now CPU is free. Okay. So you see, if the task of process P1 is over, so then what will happen? Since CPU is free, then CPU will be ultimately CPU will be given to process P2, or you can say that the CPU will be given to the process which is present in the ready queue. Okay, it means what? If a process makes a transition from running state to terminated state, so this transition will lead to a different process to make transition from ready state to running state. Okay. So you see here, this process was initially in the ready state. Since the CPU is given to this process, so it means what? Now this process is in the running state. Okay. This process was initially in the ready state. Okay. And when CPU got free, so CPU is given to this process. So now this process P2 is in the running state. So it means what? When P1 made a transition from running state to terminated state, okay, running state to terminated state. So P2 made a transition from ready state to running state. So you got it. So it means what? This statement is wrong, because here it is written, if a process makes transition D, it would result in another process makes transition A immediately. Not transition A, but transition B. Here it would be B, not A. Okay. So this option is wrong. Are you getting it? Or there is another explanation. You see, once again I tell you, there is one more explanation left. Suppose you see, let me rub this. Yes. Suppose you see, a process P1 is running, and the task of process P1 is over. And the task of process P1 is over. So now process P1 is gone. Okay. So it doesn't mean that if the task of process P1 is over, then P3, this process is in the hard disk. It means what? It is start state. P3 is in start state. So it doesn't mean that P3 will make a transition from hard disk to main memory. Okay. Maybe P3 doesn't, maybe P3 doesn't require to run. Okay, so it will remain in the hard disk. So it doesn't mean that if a process gets terminated, then another process from start state will move to ready state, or we can say that another process from hard disk will move to RAM. Okay, it's not necessary. Okay. But it's necessary that if one process gets terminated, then CPU is free, then CPU will be given to the another process. So that another process means what? P2 will make a transition from ready to run. Okay. So that's why statement number 1 is false. And you see what is statement number 2? A process P2 is blocked can make transition E, while another process P1 is running while another process P1 is in running state. Okay. So let's analyze this statement. A process P2, okay, a process P2 is blocked. Here it means what? A P2 is in blocked state. Can make transition E. This block state can make transition E. Means what? Block to ready. While another process is in running state. So let's analyze this one. So here you see, it's a RAM. Okay. So here there are 3 processes: process P1, process P2, process P3. So P1 is in running state. CPU is with P1. Okay. So now, here I will write P1 because P1 is in running state. Process P2 is blocked with IO. Okay, and yes, so that's why process P2 is in blocked state. Okay, and process P3 is doing nothing, it's simply in the ready state. Here is process P3. So you see, if a process P2 is blocked, here you see process P2 is blocked, it can make transition E. It can make transition E means what? Block to running, while another process P1 is in running state. Okay, you see, here you see process P2 is blocked. Okay, then definitely if the IO task of process P2 is over, then process P2 can make a transition to ready state. It means what? Just remove IO. When IO is with process P2, it means what? Process P2 is in block state. And if we remove IO, why we are removing IO? Because the IO task of process P2 is over. So now you see process P2 is simply in the main memory, it's doing nothing. It means what? Process P2 has made a transition to ready state. Okay. So here even P1 is running. P1 is busy with the CPU. Okay. P2 can make a transition from blocked state to ready state. It means what? P2 can make transition E. Okay. So statement number 2 is also correct. So you see here two statements are correct. Statement number 2 and statement number 3. I hope you got it. Okay, thank you.